What I want to spend more time about today is something that people probably have heard about these other bonds, but they probably have not heard about this one, which turns out to be really important. Before I get there, I want to say something about water. And this is where we make an important difference with the chemist, is that in chemistry, sometimes what you're doing takes place in water. In fact, oftentimes, but not always. In biology, always it takes place in water. Every living thing is mostly water. So we care about what happens in aqueous water solution entirely. So there's some important features of water that are really relevant to biology that they make less of a fuss about in chemistry because they don't always dissolve things in water. And so the structure of water, talked about a little bit. There are a bunch of different ways to draw it, all of which are about the same. This has OH bonds, that are very polar. Why? Because the electronegativity is very different between oxygen and hydrogen. Therefore, can make hydrogen bonds. Water is sort of your prototypical hydrogen bond maker. It's got really great hydrogen bond donors, hydrogen attached covalently to an oxygen. This is a special hydrogen. That's a special hydrogen. Every hydrogen on here is a special hydrogen. And those lone pairs are hydrogen bond acceptors, the other half of a potential hydrogen bond. So it's hydrogen bond city, right? And it's also very polar. That is, this is very much delta minus, and these guys are delta plus, those little partial charges. All right. So that has some very important consequences. Therefore, water can form bonds with parts of molecules that fit either of these two criteria. A, can make hydrogen bonds. I can make hydrogen bonds with them. Or B, are charged. Note that more neatly. That is ions. And this is an even stronger than A. Okay? And so this just simply follows, right? Water is polar, so it's going to and it can make hydrogen bonds. So it can form hydrogen bonds to other things that can make hydrogen bonds. That sort of follows quite directly. It also can interact quite happily with things that are charged. If I've got something positively charged over here, the water molecule is going to face its oxygen, its partial negative towards me. If I've got something negatively charged, the water is going to flip around and point the other way, but it will happily interact with things that are charged. Right? On the other hand, water can't form strong bonds with parts of molecules that are non-polar. That is, they can only do van der Waals. So if I have a part of a molecule that is not polar, that is not charged, that cannot make hydrogen bonds, water has no interest in me. The only thing water can do is van der Waals, and van der Waals we usually don't pay much attention to because it's so weak. Right? There's a question whether they're making a strong or a weak bond. What that means is that there's an important distinction. Parts of molecules that can do this kind of stuff, that can interact with water, are called hydrophilic. That is water loving. And these parts of the molecules are called hydrophobic. Exactly. Water hating. And it isn't really a love-hate thing, okay? You know, molecules don't have emotions. It's about, it all boils down to energy. Can they form bonds or not? I'm going to do a little, some cartoon. I'm going to shade in hydrophobic things dark and hydrophilic things not shaded, as we'll look at some molecules in a second. But this is a very important distinction. And what I want to do is do just a little more explaining, and then we'll talk about some examples. So the thing is, this results in a non-covalent bond. I'm going to put bond in quotes for reasons that I should explain in a second. Right? It's not a real bond, but an effect of water's properties. So let me show you what I mean by that. Okay? And what it is, it's called the hydrophobic effect. So it's not a hydrophobic bond, it's a hydrophobic effect. And the idea is that this, in water, hydrophobic parts of molecules tend to cluster with hydrophobic parts of other molecules to avoid contact with water. So I want to draw some diagrams of this in a second, but the key thing here, almost all of our other bonds were like plus with minus, opposites attract. In this case, it's not phobic sticking to philic, it's phobic with phobic. Basically, because they can't interact with water, they cluster up avoiding the water. I want to show you more what I mean by that in a second. And again, it's not because they're inherently sticky, but it's because they're avoiding contact with the water. So let me show you what I mean by that, and then I think it'll be a little bit clearer about why this is not a bond and how it works. So for example, let me give myself a little more space. It always happens. Sorry, everybody. Tablet is not as calibrated as I would like. All right, there we go. For example, ammonia is hydrophilic in a big way. If you add it to water, it dissolves. Bless you. So, if you have your little tank of water, right, this is water in there, you've got H2O and NH3 and H2O and some more H2O and some more NH3, H2O. They're all mixed. And there are many H bonds between H2O and NH3. So it happily dissolves in the water. Right? However, oil, as we'll see later on when we see its structure, is hydrophobic. It's a classic example of a hydrophobic compound. Forms droplets on the water. It does not dissolve. Right? And what you have, if you have your oil on a glob floating on top of the water. That is, so there are oil bonds and water bonds, but no oil-water bonds except poor old van der Waals. Right? So this is the hydrophobic effect. I wanted to give you an analogy for it in a second. Fundamental difference is you add, if you got a tank of water and you add something hydrophilic, it dissolves. Now, sorry about that. To be clear, dissolving does not mean the molecules of ammonia split up into their atoms. It means the molecules separate from each other and happily join the water. If you put oil on water, you typically get globs of oil on top of the water, or a thin skin of oil on top of the water, but it does not mix in a significant way. And the important thing is the oil is staying together because of the hydrophobic effect. So let me explain by analogy. So when I was an undergrad at MIT, I was not my suave, personable self. I was a rather nerdy guy. And so I know you can't imagine how that could be true. But so one time, some of me and my nerdy buddies went to a fraternity party, God help us. And we arrived there, and we had nothing to contribute to the party, right? We didn't know what to talk about. We didn't drink a whole lot of beer. So we ended up, a lot of us, playing pool that night. I had a great time playing pool, but didn't socialize with the fraternity folks. And it was not because they repelled us. It's because we had nothing to bond with them over, right? Whereas when their fraternity buddies came over, they joined the party, all right? And they could move freely among the people at the party, and they had a great old time. And that's sort of like what's going on here. So because the ammonia molecules have something to contribute to the party, they can bond with water molecules, they can shift, they can join the party, they dissolve into the party, right? Me and my nerdy buddies, it wasn't that we were sort of nerds attracted to nerds. It was and it wasn't because the fraternity people said, no, you can't join the party. It was more like we had nothing to talk with them about, and they had nothing to talk with us about, and so we ended up together, all right? And so it's not, the oil sticks to the oil, not because it's sticky. I mean, it's got van der Waals, but we won't count that. But it's because it can't get drawn into the party. It can't get drawn into the solution with water, because there's nothing about the oil that's interesting from water's point of view. That is, water says, I'm interested in things that can make hydrogen bonds, I'll drag you into the party. If you're charged, I'll drag you into the party, that's great. There's nothing about oil that's either charged or can make hydrogen bonds. And as a result, it stays by itself, okay? And so again, it's not a bond. It's not like the oil's so much sticking to the oil, and it's not really even so much the water's repelling the oil. It's just they have nothing to do with one another. They're sort of separating one from the other, right? And it turns out this is not, beyond the reason I tell this embarrassing story about myself is not so much, is because this is actually important. Otherwise, I could just embarrass myself for other reasons. But this force will turn out to be really important in a whole bunch of different things that we see in biology, because everything takes place in water. So before we go on to some examples of this, question.